Hello, welcome back. Today let's focus on the concepts of magnets, magnetic fields, and magnetic forces. All right, so I'm going to share my screen. So what causes magnetism, right? And why do certain things experience magnetic forces and other things don't? Okay. Seems like it's a little bit of a mystery, even though we have experiences with magnets in our everyday life. The reasons for why something is magnetic are not always very clear. So in today's lecture, let's focus on magnets, what causes magnetism, and why certain objects experience a magnetic force. So as I mentioned, we've all had experiences with magnets, right? You may have put two magnets close to each other, the North Pole is close, and saw that the magnets repel. If you flip them around, you would see that the North Pole of one magnet would attract the South Pole of another magnet. And it's a very common thing that we see, that we've played with magnets before, right? Even a compass is a magnet, right? So how does a compass work, and why does that compass always want to point in the same direction, which is north? Even on our everyday refrigerator, right? We see magnets. Why do they stick to the refrigerator and not other objects, right? Why do they not stick to our cabinets or other metals even? Right? What is the reason behind that? And there's also lots of different shapes of magnets that you might have played with in your everyday life. Horseshoe magnets are a common one, bar magnets are another common one. So, we see magnets all the time, but how does magnetism work? To talk about magnetism, we need to talk about magnetic fields. Okay? When we talked about electricity, we first talked about electric fields, right? And what causes electric fields and how an electric field can produce a force. Right? You need a charged particle to create an electric field. And once that electric field is created, if there's another charged particle in that electric field, it's going to experience a force, an electric force. Similarly with magnetic fields, okay, you basically see two things happening. Magnetic fields, you need a charged particle, but you need a moving charged particle to create a magnetic field. Once that magnetic field is created by the moving charged particle, if there's another moving charged particle inside that magnetic field, it will experience a force, a magnetic force. So there's kind of two things that need to happen. First, I need to have a moving charge to create a magnetic field. And then there's another moving charge inside that magnetic field that will experience a force. Notice that the charges are moving now, right? With electric fields, the charge can be stationary and you have an electric field. And if there's another charge inside that electric field, even if it's stationary, it will experience a force. With magnetic fields, it's a little different in that you do have to have a charged particle, but that charged particle has to be moving, has to have a velocity to it. Only then will you have a magnetic field, and only then will you have a magnetic force. If you have a magnetic field and you put a charged particle in there and it's stationary, it's not going to feel a magnetic force. Okay. So that's the key difference between the electric field and the magnetic field, in that the charges have to be moving in order for these effects to be seen. So what actually causes magnetism? A moving charge produces a magnetic field. That's the first step. This is a picture of a charged particle. It's positively charged. It's moving to the right, so its velocity vector points to the right. The electric field points radially away from that charge, right, because it's a positive charge. But now, since the charged particle is now moving to the right, it also produces, in addition, a magnetic field. And these blue lines, these circular blue lines, indicate the direction of the magnetic field around this moving charged particle. If this charged particle became stationary and stopped, it would still have an electric field around it, but it would no longer have a magnetic field around it. Okay. So we know from experiments that moving charges produce magnetic fields. But you might be wondering, well, when I stick a magnet onto my refrigerator, I don't see any moving charges there. Everything's stationary. And there's a magnetic field happening and a magnetic force happening. Why is that? And it's a really good question because these two things seem to be very contradictory, right? Moving charges producing a magnetic field, but you have stationary magnets sticking to a stationary refrigerator. Nothing's moving here. What's going on? What we're actually seeing is a microscopic effect. In fact, it's a quantum mechanical effect. Quantum mechanical is so small. It's a very small effect. In that, if you look inside these magnets and you zoom in on them, you will observe the electrons inside these magnets. And the electrons are spinning themselves and they're also spinning around the nucleus of the atom inside these magnets, right? And there's a lot of them. We're only showing one in this bottom picture. But these spinning and orbiting electrons are moving charged particles, right? And we said that a moving charged particle creates a magnetic field. So inside these magnets, these moving charged particles are creating little tiny magnetic fields. And all of those little tiny magnetic fields produced by all those little tiny spinning and orbiting electrons, when you add all of them up, all of those magnetic fields up, it creates one big giant magnetic field in your little stick magnet that you stick on your refrigerator. And that magnetic field interacts with the metal on the door of your refrigerator, and the two things are attracted to each other, and you see stick together. And the next logical question you might ask yourself is, well, don't all materials have spinning electrons and orbiting electrons in them? Why aren't all materials magnetic then? Well, it's because only a few special materials can become naturally magnetic. Most of the time, the electrons that are spinning around these atoms are very random, right? They're spinning in lots of different random ways, and all of their little tiny magnetic fields basically all cancel each other out because they're all randomly spinning around in different directions, and there's no overall macroscopic effect. But with certain materials like iron and cobalt and nickel and some metals that have a lot of iron in them, or cobalt or nickel, those are very unique materials, and that the spin of the electron and the orbit of the electron, and in fact the whole, there's actually little regions within these magnets, they actually become lined up in the right way. All of their tiny little magnetic fields become lined up in the right way, and that only works for certain materials that can become naturally magnetic, like iron and nickel and cobalt. And there's other ones too, but I'm just giving those common ones. Those materials are very unique and very special, and that their little magnetic fields of the electrons in those materials can become lined up in such a way that all of those magnetic fields are pointing in the same direction, and they all add up and you see a big, giant, macroscopic effect of a magnetic field. So that's why not all materials are magnetic. Only certain ones can become magnetic. And notice that the spinning electron, or this orbiting electron around the nucleus, there's an N and an S here. And you might already guess what that means, the North Pole and the South Pole. So that brings me to the next slide. Let's think about the magnetic field and how can we kind of visualize what the magnetic field looks like? Well, what we use is magnetic field lines. Before we used electric field lines, and now we'll use magnetic field lines to represent the direction of the magnetic field. Now, if I look back on this little electron, right, there's a north and a south. That means that the magnetic field points out of the north pole of this particular electron and back through to the south pole of that electron. If you look at a bar magnet, you'll see the same thing, a north pole and a south pole. That means that all of those little magnetic fields of those electrons are lined up in such a way that all of their north poles are pointing in this direction and all of their south poles are pointing in this direction. And north and south pole is just arbitrary names we give these things to tell us that there's a magnetic field pointing out or away from the North Pole, circling back around and into the South Pole again. And that's what the magnetic field can be visualized by, as these magnetic fields. And notice, take a look at this. This is another unique thing about magnetic fields, is that their magnetic field lines form closed loops. Notice every single one of these magnetic field lines loops back around back through the magnet. They never end. They form closed loops. This is a little bit different than electric field lines because electric field lines start on positive charges and they always end on a negative charge. So electric field lines have a beginning and an end, whereas magnetic field lines actually form closed loops. And they emerge from the North Pole and they loop around back through the South Pole again. Interestingly, the Earth itself is a magnet. They're not exactly sure what causes the magnetic field of the Earth, or there are a couple of theories. The most important thing to note is that the center of the Earth is an iron core. And remember, iron is a magnetic material. And it's also spinning, right? There's a lot of charged particles, it's iron, and it's spinning, and it's moving. And it might even be a liquid core down in the very center. So because of that, that could be what's causing the magnetic field of the Earth. And the magnetic field lines come down actually into the geographic North Pole. They go through the center of the Earth and they come out the bottom near the South Pole. So the geographic North Pole of the Earth is actually the magnetic South Pole. So this is how we can visualize magnetic fields, right? That's the first step. We have to think about what causes a magnetic field: moving charges. Okay? And this is what the magnetic field lines look like for a bar magnet or for the Earth. And for the simplest case of a bar magnet, we call this a magnetic dipole. Dipole meaning, di means two, right? So there's two poles. Poles just mean two extremes, one end to the other end. It's a magnetic dipole. It has a north end and a south end or pole. And if I cut this magnet in half, what I would end up creating is two more magnets with a north pole and a south pole. And if I kept cutting it again, if I cut this one in half again, I would get a north pole and a south pole and a north pole and a south pole again. And in theory, I could do this infinitesimally forever until I got down to the very end. And then I would get down to a single electron, and we know that one single electron has a north pole and a south pole to it as well. The key here is that I can never just get one pole by itself. They always come in pairs, north and south. Scientists have never been able to locate just an object with a single north pole. It doesn't exist. If you have a north pole, it's going to have a south pole along with it. Okay. So if I have a bar magnet, right, and I don't know if you've ever done this experiment in your classes before, but if you sprinkle iron filings around this magnet, you will see that the iron filings line up with the magnetic field of this bar magnet. Iron is a magnetic material, so its little electrons are all lined up nicely, and those little electrons, the little magnetic fields in those little tiny electrons in the iron filings, want to line up with the magnetic field lines of this big magnet right here. We see the same effect when we use a compass, right? The three most magnetic elements on the Earth are iron, cobalt, and nickel. Those are the very special materials that allow natural magnetism to occur. They have electrons, and their spin and the orbit of the electrons are such that they can become nicely lined up, and all of their tiny little magnetic fields can add up together instead of cancel each other out. And as I mentioned earlier, the Earth itself is one big giant magnet. And the North Pole is actually the magnetic South Pole. And the South Pole is actually the magnetic North Pole. And those magnetic field lines are shown here in the picture below. And so anywhere I have a compass, which is basically a magnet, the compass itself, just like those iron filings around that bar magnet want to line up with the magnetic field, the compass will also do the same thing. It will line up with the magnetic field of the Earth. And that's what's showing here. If I'm using a compass here on the Earth, it's going to tilt up towards the North Pole. And another interesting tidbit is that Earth's magnetic field is actually responsible for the beautiful auroras, the northern lights or the southern lights that we see. There are ions, charged particles coming in from the sun, right? So a moving charged particle comes in, it interacts with the magnetic field, it can gain a little bit of energy from that interaction, experiences a force, it gains a little bit of energy, and those charged particles release their energy and they kind of fall back down into a lower energy level. They release light, and that's why we see these beautiful colored lights. And it happens mostly at the North Pole or close to the South Pole, because that's where the magnetic field is more tilted on those ends, as you can see. So the effect becomes more extreme there. So the magnetic fields of two bar magnets, for example, as you've seen before in your everyday life, those magnetic fields can interact with each other, and there can either be a repulsion or an attraction. Like poles repel one another, as I'm sure you probably all know, two north poles will repel each other, two south poles will repel each other, but if I put a north pole near a south pole, there will be an attractive force, which means that there's a magnetic force happening here due to the fact that there's magnetic fields interacting. This force, the magnetic force, depends upon the strength of the magnet, all right? So how well is this thing magnetized to begin with? And also depends upon the distance between the two poles, right? The closer I bring the two poles together, the stronger the magnetic force will be. And in the same vein, the stronger the magnets, the stronger the force will be. If you want to learn more about that in depth, look up the Biot-Savart law. In particular, the force drops off as 1 over r squared. So as I bring these magnets closer together, the distance goes, the radius or the distance between these two poles gets smaller and smaller and smaller. The force and the distance are inversely related to each other. So as the distance gets smaller between the two poles, the force is going to get even bigger. And that's what's shown here on this graph. This is a 1 over r squared graph. As the distance gets very small here, the force gets big. And as I bring the two poles further away from each other, the force drops off as 1 over r squared. This is very much like the electric field. The electric field also drops off as 1 over r squared for a single stationary charged particle. So as was mentioned, moving charges are what create magnetic fields. But if I have a bunch of moving charges together, if you remember, we call that an electric current, right? So if I have a current carrying wire, that means that there's just a bunch of moving charges moving in this wire, right? So a current carrying wire actually produces a magnetic field around it. And this is one of the famous experiments in physics, Oersted effect. Oersted noticed that when he brought a compass near a current carrying wire, the compass deflected. And he thought, what's going on? Well, in fact, what's happening is that this wire, which has a bunch of moving charges in it, produces a magnetic field around it, and that can make the compass go off track, right? Because the compass is not only sensing the magnetic field of the Earth now, it's sensing the magnetic field of the wire. And this picture down here below in the bottom right shows the direction of the magnetic field around a current carrying wire. So what this is showing is actually if you have a straight current carrying wire, you can envision the magnetic field around that current carrying wire by pointing your thumb of your right hand. Okay. Key here is to always use your right hand. Take your thumb of your right hand and point it along the direction of the current in the wire. Right? So in this wire, the current's going up. I point my thumb upward, and I curl my fingers around the wire. The way my fingers curl is the direction of the magnetic field around the wire. And so here are the magnetic field lines around the wire. They get further apart as I get further from the wire because the magnetic field drops off as I get further from the wire. And they get closer together as I get closer to the wire to indicate that the magnetic field is strong near the wire. So if I have a current carrying wire, it produces a magnetic field because it's basically just a bunch of moving charges, which is what causes a magnetic field. So here's a magnetic field for a single charge moving to the right. It loops around. For a current carrying wire that the current goes straight up, the magnetic field lines will look like this. So it will form closed loops around that. But there's other configurations of current carrying wires as well, right? What if I had a loop of wire? The magnetic field for a loop of wire, so the wire here is indicated with the gold material. And the current is going, I guess from my vantage point, it's going counterclockwise. The magnetic field for this particular configuration of moving charges that are going like this in a circle looks like this. You got the North Pole, you've got magnetic field kind of pointing outward like this, pointing up through the loop and out of it. So that means that the North Pole of this loop actually is pointing kind of upward on the top. The South Pole is on the bottom. Remember, magnetic fields always come with North and South Pole together. And you can envision that these lines actually never end. The picture doesn't draw all of them because it's just too hard to draw all of the lines. But you have to envision that these lines actually never end. They just keep looping. And this is what the magnetic field looks like for this kind of configuration. And so it's a three-dimensional thing. It's a little bit hard to visualize, but it's three-dimensional. What happens if I put a bunch of loops of wire together? So let's suppose I stack a bunch of loops on top of each other and they're all carrying current. So it looks something like this on the bottom. I have a current carrying wire and I just loop it a bunch of times. Stack up those loops and I put a current through it. What's the magnetic field going to look like in this case? It's going to look something like this, shown with the blue. Again, these lines never end. They just keep looping back around. This is called a solenoid. And a solenoid is actually a very useful circuit element for many purposes. If you ever take a class on circuits, you will learn a lot about solenoids. The nice thing about the solenoid is that if you look inside all of these loops, the magnetic field inside here is nice and is pretty much almost straight, right? If I look right in the middle here, the magnetic field is almost straight. And it's also very uniform. It's pretty much evenly distributed, nice and even throughout the middle of the solenoid. So a solenoid gives me a nice, straight, uniform magnetic field inside, which is nice. These are just a few configurations for different setups of moving charges, right? You got a straight line of moving charge current, you got a loop of moving charge, or you got a bunch of loops of moving charge. These are the common ones. And these are what the magnetic field looks like around each of these configurations. Now, what happens now, right? So I've set up a magnetic field. Okay, I've got a moving charge, whether it's just a single charge or a current, right? That's going to create a magnetic field. Okay, but now what? Well, if I put another moving charge inside of that magnetic field, there's going to be a magnetic force happening. Okay. So magnetic fields are created by moving charges. And by the way, the unit for the magnetic field is a Tesla, capital T, Tesla for the scientist, Nikola Tesla. If I place another moving charge within that magnetic field, it will experience a magnetic force. The magnetic force is just like any other force. Its units are newtons. Okay. And I have two equations for the magnetic force. Okay. The one on the left is telling me what is the magnetic force, so force F, on a single moving charged particle inside a magnetic field. So this one on the left-hand side is the magnetic force on a single moving charged particle in which The velocity and the magnetic field are perpendicular to each other. The velocity v and the magnetic field we denote with the capital letter B, by the way. Don't ask me why. But the magnetic field is denoted with a capital B. And for this equation to work right here, the velocity and the magnetic field are perpendicular to each other. If the velocity and the magnetic field are in the same direction or even anti-parallel to each other, you will not have a magnetic force. Okay, there has to be some part of the velocity and the magnetic field that are perpendicular to each other for this equation to work. And this one will work if the velocity and the magnetic field are completely perpendicular to each other. Q represents the charge. And that would be in coulombs. This doesn't tell me anything about the direction of the force. It just tells me the magnitude. We'll get to the direction in a minute. Similarly, you can also think about this is the force on a single moving charged particle, but if I have many, many, many moving charged particles, I've got a current, right? And so if I have a current carrying wire and I place it inside a magnetic field, it's also going to experience a force. And that force is going to be found using this equation, where this is the magnetic force on a straight current carrying wire. I represents the current. This L, lowercase l, is the length of the wire. And B is the magnetic field. In these units would be Tesla. And again, in this case, the direction that the current is flowing and the magnetic field direction are perpendicular to each other. Current direction and magnetic field B are perpendicular to each other. In order for this equation to work. If the current flow and the magnetic field are parallel to each other or even anti-parallel to each other, there's not going to be any force felt on the wire. There has to be some component of the current that is pointing in a direction perpendicular to the magnetic field in order for there to be a force occurring. Again, this tells me nothing about the direction of the force, just the magnitude. Now, if I want to know the direction of the force, we use another special funny right hand thing. Remember how we used a right hand thing for the magnetic field for a straight current carrying wire? There's another right hand thingy that we have to do. They're called right hand rules, by the way. And we have a lot of them in physics, especially when we're dealing with magnetism. If I want to know the direction of the force on a moving charged particle in a magnetic field, one way to do it is to use your right hand, and you take your right hand and you point your thumb along the direction, you point your index finger along the direction of the velocity of the moving charge. right? So in this case, the moving charge would be going to the left. So that's its velocity vector. You're still using your right hand, and then you point your middle finger in the direction of the magnetic field. So in this case, the magnetic field is kind of almost coming out of the board or out of the page or out of the screen. And notice that they're making a right angle with each other. The velocity and the magnetic field, B, are at right angle to each other. Velocity is to the left, magnetic field is out of the screen. What's left is my thumb is pointing up. That's the direction of the magnetic force, F. Okay. And this is assuming that the charged particle that's moving to the left is positive. If it was an electron with a negative sign, you would have to reverse the direction of the force. Let's do a little practice. Let's try the same thing with a current carrying wire, a straight current carrying wire. Let's suppose I've got a wire that, here's a portion of the wire, and it's carrying current to the right. And let's suppose that the magnetic field is pointing up. I will denote that with a capital B. So this is in a uniform magnetic field that's pointing up. Try to use the right hand rule method to figure out the direction of the force on this current carrying wire. Pause the video, take a moment, and then we'll go over it together. Let's use the right hand rule for this. So we're going to take our right hand and we want to point our index finger in the direction of the moving charges. In this case, the moving charges are in the direction of the current. So we're going to take our index finger and point it to the right. It sometimes gets a little wonky. Okay. Now we take our middle finger, and it has to be pointing up. So my index finger is pointing to the right, my middle finger is pointing up. Where's my thumb pointing? Out towards me, out of the screen, out of the board, towards me. It's very hard to show you on the screen, but index finger to the right, middle finger is upward in the direction of the magnetic field, thumb is coming out. Okay. That means that the force is going to be coming out of the page. So this length of wire is going to feel a force. Its magnitude is going to be current multiplied by length multiplied by magnetic field. That's going to be the size of the force. And the direction of the force is out of the board. It's tricky. But there's lots of right-hand rules. And actually, it's very neat because it becomes a three-dimensional thing and you can start to visualize the velocity, the force, the magnetic field. I have another question for you. We already talked about a loop of current, right? And this loop of current has, the current is going counterclockwise and the magnetic field looks like this. It points upward through the center of the loop of wire. Okay. So that's the magnetic field for this loop of wire. Let's suppose I take this loop of wire and place it in a uniform magnetic field that points to the left. So I'm taking this thing and I'm putting it in another magnetic field that points to the left. So the magnetic field that's the external uniform magnetic field points to the left. And here's the magnetic field for that external magnetic field. What's going to happen? I'll give you a hint. The loop is going to rotate. The question is, which way is the loop going to rotate? Pause the video, think about it for a second, choose an answer, and then come back and we'll talk about it. I'll give you one more hint. Think about the example with the iron filings within the magnetic field of the bar magnet. What did they do? The iron filings lined themselves up with the magnetic field of the bar magnet. The same thing is going to happen with this loop. This loop of wire, there's a current flowing, there's a magnetic field being produced. Okay. The magnetic field produces, magnetic field has the North Pole pointing this way, the South Pole is down here. What this wants to do then, just like the iron filings line up with the external magnetic field due to this bar magnet, this little loop of wire is like a tiny little iron filing, right? It has its own magnetic field in it. It wants to line up with the external magnetic field that it's in. So it's going to rotate this way. It's going to rotate until this loop, which has its own little magnetic field because it has current flowing in it, this is going to line up with the external magnetic field that's pointing this way. And once it lines up, it'll stop rotating. It's a very interesting effect. But it's actually the basis for an electric motor. So this has very, very important implications for us. What is this little animation showing? Well, this bottom part here is a circuit, right? Here's the battery. There's electricity flowing. Current is flowing through this loop. All of this loop right here, see this loop? It's a big giant circuit, okay? So there's current flowing through this loop. Because there's current flowing in this loop, it has its own magnetic field, right? Just like this loop of wire had its own magnetic field. Okay. But let's suppose I take this loop and I put it, Alexa's trying to talk to me. Let's suppose I take this loop and put it inside another magnetic field, just like we did here. We took this loop and we put it inside another magnetic field. What happened? It rotated because it wants, these two magnetic fields want to line up, right? That's exactly what's happening here. This current in this wire is creating its own magnetic field. That magnetic field, it's like a little tiny compass, right? Or a little tiny iron filing. It wants to line up with the external magnetic field that it's in, which is denoted by this capital N and S, right? I got a big giant magnet and I place this current carrying loop inside that magnet. What's going to happen is it's going to want to rotate. Okay, and it will. Now the setup, before we said eventually it'll rotate and it will eventually stop, right? Once they're lined up, it's going to reach like its lowest energy and it's going to want to slow down and stop. But the way this setup is that this circuit allows this thing to actually keep rotating under its own inertia. So it occasionally the current stops flowing for a moment, and then the loop just keeps going that way because it was already rotating that way to begin with. And then once it rotates, the current starts to flow again, and the whole process keeps going and going and going. It seems kind of complicated, but actually all you're doing is taking a tiny loop of current, place it inside on a magnetic field, and it's going to spin. I find it amazing, right? That's the basic electric motor. What we're actually doing here is converting electrical energy and magnetic energy into mechanical energy. The thing is spinning, right? It's a mechanical thing, right? I can connect this motor. This actually the coil, this rounded part is called a rotor. Okay. I can connect this rotor to some other thing and spin it. And that's going to allow me to do lots of different things, right? I think it's cool because it just seems so simple, so basic. But that's the basic idea behind an electric motor. It's amazing. And in the next chapter, when we talk about the relationship between electricity and magnetism, we will see that we can actually go the other way. We can start with mechanical energy, spin a loop of wire inside a magnetic field, and we can spit electricity back out again. That's called a generator. But we'll talk about that next time. I hope that this little lecture helped a bit, uncovered the mystery a little bit of magnets and how magnets are created and how magnets interact with other magnets. It all comes down to moving charges create magnetic fields. Other moving charges interact with that magnetic field and feel a force. That's all that's going on. I'll see you next time.